do good for you. You know, all right. Hi, everybody. I'm Danny Quist. Can you hear me? Am I microphoning correctly? I can microphone even better. Is this better? How you feel back there, Adam? You're way in the back. You good? Okay. You can hear me, though, right? That's what I was asking. Okay. So I'm going to talk to you about reverse engineering Go. So just as a show of hands, how many of you have seen what assembly looks like in real life, like perhaps in a text file? Okay. How many of you have actually written the sacred language? Okay, good. So I'm talking to friendlies here, so we're gonna do that. If you find yourself lost, just kind of like pat your head or something like that, and I'll try to pay attention to the audience, and then I'll put it in terms of like dinosaurs carrying eggs or something like that. So I'm a little nervous about the technical content, so we'll go ahead and get started. Who am I? Currently, I work for a very small, very new startup called Unit 129. This is one of my first forward engineering jobs. Usually I'm a reverse engineer. So, you know, actually writing code is a lot harder than tearing it apart. In my past, I've been a reverse engineer. My specialty is weird malware. So anything new, I love, any puzzles, that sort of thing. I also do code author attribution, tell you who wrote it. And then if you need source code for binaries, I can extract it out. And I also teach a reverse engineering course at a university, and I haven't been fired yet, so that's it's been like 2 months. Past, worked at Redacted. That is the actual name of the company, and it is dead. So lots of sad memories. See some redacted people in the audience, so hello. Previous to that, I was at Bechtel, MIT's Lincoln Lab, and Los Alamos National Lab, and please don't judge me, I got a PhD. Okay, so what we're going to talk about today is how to reverse engineer Go malware. And if you've has anybody tried to look at a Go malware ever? Or any Go sample? Yeah, kind of a pain, isn't it? Yeah, nothing works. So I'll go through like my method about how I got it to work and show you just like a general overview. And then what we're going to do is we're going to talk about BianLian, which is a ransomware group. And if you were here last year, there was an excellent talk on the tactics, techniques, and procedures, and all the network monitoring and everything like that. This is the add-on talk. And also, just as a side note, this is what happens when your company doesn't have a marketing department to shoot down talks, because this was supposed to be last year. But anyway, that's a little trivia. Okay, so what we're going to do is we're going to use analyzing malware as a practical example for learning how to reverse engineer Go malware. Okay, so here are my problems reversing Go. And if anybody else has any things, please jump in. So most of the reverse engineering tools assume that the code you're looking at is written in C or C++, which is fine because most of it actually is. It's pretty rare that you find Go or anything else that's outside of there that comes in. Once you get into some of these languages, it's all about finding the libraries, because it turns out nobody writes their own linked list or their own dictionaries or arrays or hash tables, whatever. They all use the stuff that's built in. And so figuring out what is author written code versus library code is kind of the primary problem that we're looking at. And just to belabor that point a bit more, when you're reverse engineering malware, it turns out that they're, as a rule, very terrible software engineers, so they don't write much code. And so like when you do find their code, it's usually small and very compact and terrible. So, well, and I really shouldn't be too critical about that too. You guys haven't seen my code, so maybe you have, I don't know, it's bad. So things like you wanna convert strings, copy them, convert from ASCII to Unicode, which is a pretty common activity on Windows, that sort of thing. Go does all of this. And actually any language, like if you could actually apply this to Rust if you're gonna be looking at that, or a Haskell program. There's basically no flirt identification. So you're kind of in the roll your own, invent the internet stage here. Furthermore, like any modern language, it does a lot of stuff for you. And by do a lot of stuff for you, it means there's a lot of boilerplate code you gotta skip over. And then it's also aggressively optimized by default. And things like types are not compiler constructs, despite the language implying everything is. And then compiler inlining is just, it's competitive and vindictive in the Go compiler. So You just got to watch out for that as you're translating the assembly back into something that makes sense. I mean, really, the problem is that Grismer, Pike, Thompson, those are smart people, and they wrote a really good language, and so now it's up to us to like try and figure out what's going on. Great. So what's the process? High level, we're gonna, whenever we're looking at a sample, this kind of applies to anything right here, but essentially what we're looking for is any of the strings. We want strings because that's what your APIs use. When you're opening a file, you do not pass it a base 64 encoded text unless you're using some garbage thing like Java on a mainframe. Then maybe it does it for you, but for the most part, you have to pass strings to C APIs. You got to get it. At some point, they're going to want to write an extortion note because, like, in theory, they're trying to make money here. So, like, that's got to be plain text. So there's got to be some decoding and some actual plain text at some point. And so your job as a reverse engineer is either to just look at the ones that are embedded in the binary and draw conclusions, or decode them and then start to do the same thing. The next thing is that you want to find the code that's actually written by the malware author. When we load up a Go binary, it's like 4.5 megs. And it's like 4.5 megs for just a hello world. It's a lot, right? And granted, that's like not stripping the executable, all the debugger stuff is enabled, and probably a lot of things that I should get out of it, but it's very big files. But most of that is actually library and runtime that's added by the executable. So you have to be able to identify those and eliminate it from your analysis. So how do we do that? And I'm kind of focusing on this as like you've never looked at a Go malware before and you need to like refresh yourself on how this works. This is just like my process for learning how to reverse pretty much anything. So you start off with easy mode. So we're gonna make a test program. We're gonna print a string. So basically you can do anything you want inside of here. You can read and write to a file, you can call a function, you can loop over a variable, that sort of thing. In the upper right-hand side, this is a little bit of an eye chart, but this is the Go code. This is garbage Go code, but it's just like a print thing. And all I'm doing is I'm just making a test executable that I can drag into a disassembler and see what it looks like. And the idea, and so this is how you compile it, I believe right here. And then the symbols here, when everything looks good and you're looking at your code for a very simple thing, you will find the symbols for something called main.main or runtime.main or not runtime.main, but like one of the, something that looks like the start for your program. And so this is a good sign. So we've basically put some things that we know about inside of an executable, and we're gonna try and learn and see what it looks like. So just looking at a Go executable as it's running and looking at strings, strings are the reverse engineer's crutch. But just on a normal one, you can see lots of things built in here. So there's a couple things that are interesting. The first one is this Go build ID. This is an identification string that's made every time you compile a Go executable. So this is a fairly good indication that you're dealing with a Go binary because a lot of the internal Go stuff requires this. The next thing you'll see is a lot of strings that look like they come from standard libraries that have been inside of executables. So this is all normal. The way that Go works is that it builds up a string table. It doesn't necessarily have the null byte at the end of all strings. So what you'll see is them all flushed together. And so you'll see things like flags to various API calls along with things like your command and control type stuff. The other thing to look for as you're compiling or looking at compiled Go binaries is that there'll be lots of strings inside of here. So as all of the libraries are linked in and the other runtime elements are copied in, it includes the file path. So this isn't anything that it needs to actually run, but it's usually included. So for my executable, this is running on a Mac with Homebrew, so it's running out of my directory up there. It encodes my directory in, and unless a malware author specifically goes through and edits the strings, there's not really a good way to take it out. So these are just some examples. So when things are going well, you'll see strings along these lines, and this is what it looks like. So when you get inside of a disassembler, this is what it's gonna look like. If you're wondering which disassembler it is, it's the best one. It's Binary Ninja. Ghidra is good because it's free, but if you get some money, get Binary Ninja. Their decompiler is the best, and Jordan is like much nicer than the other pro people. So That's my plug. I'm not being paid by them. I just like their code. Anyway, so if you've never seen assembly, this is what it looks like. There's standard calls. You can see strings inside of the executable, so you just pull it out. It looks pretty normal, and you read it like you would just normal API calls. There's a lot of like print lock and unlock, and then there's special things for printing strings and printing lines and that sort of stuff, but this is all boilerplate. Looking at the assembly, Go also seems to fetish moving around large pointers and XMM instructions for string copy, so be aware of that. So that's there. So it all comes out pretty straightforward, and if you actually use a decompiler, it does not look like garbage. So, I mean, there's a lot of calls that you would not see in normal Go code, like I had in the previous example, but it does a pretty good job of figuring out what the parameters are to functions, pulling out the strings. It doesn't do a good job of separating out all the Go string intrinsics, but really, who cares? I look at binary hex dumps all day. It's not a problem to pull that out. So this is pretty easy, right? Like if you get the code back to normal, you can just almost read it, provided you can read code. Okay, so just to start the process a little bit, or like to overview the process, we're gonna start with a normal executable, and then you can start to add other programs. So there'll be some open source stuff, so pick a project on GitHub and just disassemble it, see what it looks like, especially if it includes libraries or links a lot of things, just to see how it does it. But what you need is like a set of gradually more complicated programs to lead you gently, step by step, through this, especially if you're recovering from COVID and have brain fog and that sort of thing. Having a real simple sample like BianLian is a great way to start learning. Okay, so my recommended learning path, if you're looking at this, is to start out with the August 2022 backdoors and tools. This is kind of when they first came out. Basically, it was, the code looks like they spent 2 weeks writing code with a six-pack, or weekend writing code with a six-pack of beer. Is about the level of quality and complexity that it has. So it's not too bad, but like actually figuring out where the code you want to look at is the difficult part. There have been a couple of updates based on some events. The other one that I recommend looking at is the January 2023, so about a year old. That's a good version of that. Same tooling set, new versions of Go, and then recently the latest sample is actually it's actually quite exciting. These guys are not good at building tools, and so like they just discovered an obfuscator. So they're now using the Go garbled module to make things a little bit more difficult, but turns out those are hard to use too. Okay, so I stand on the shoulders of giants that have done a lot more work on investigating and looking into these people and tracking them down and doing a lot of the TTP investigations. I'm just a reverse engineer, the malware guy. I just want to say, recognize the work that Sean Patty and Hallie Shukai, I think I said that right, did last year with their BianLian talk. It was excellent. I recommend you go back and look at that if you want to learn anything about how they operate and how bad they are at life. We wrote a couple blog entries about it, overviewing the initial Go execution that kind of dropped it out, or like got the actual IOCs out into the public, made them a little bit more aware, which brought some attention to them. And then Avast, the antivirus company. Does anybody here actually use Avast? No? No, I don't. Like, I don't. Right, maybe it's in Europe. Maybe I just like too American biased, but I just don't. Like, they do good work. Like, their analysts are amazing, and they wrote this decryptor for BianLian that basically all you have to have is a copy of the executable and an encrypted file and an unencrypted file, and then you just go, right? It just like figures out the key and unencrypts everything for you. It's great. Excellent work. I just don't know how to give them money because I've tried to like buy their product and it's hard too. So if anybody has any tricks about that, please let me know. And then the next thing is we talked about how they've evolved after their encryptor got hacked, how they changed their tactics. But really, primary authors here are going to be Brad Pittick, Lauren Fivison, and many other shy people. So we'll get that out there. Okay, so what is a BianLian? Has anybody been to Shenyang? Here's my theory. I think somebody went to Shenyang and said, hey, like, we gotta name our ransomware gang, so what are we gonna do? Well, those mask things were great. That's very hacker-ish, putting a mask on and hiding. Let's call it that. That's just my hypothesis here. I don't know if that's the truth. But it makes for colorful slide stuff, so you get to look at this right here. The key thing about this is it's Chinese theater, and I'm not the most culturally adept person, but they wear masks and dance and carry on quite a bit. It's supposed to be great. Never seen it, seen the pictures. So the way that they started out is that they started with, they're a ransomware group with like super flexible ethics, like all of them. You know, hospitals, schools, those are all in scope. The way that they started is in June 2022 was their first victim. July, they started their leak site, and then they started just breaking into anybody they could with money. And the key thing that we noticed is that they looked really good at their initial access. Like, they're living on off the land techniques, initial break-ins, everything was just like textbook, how you should do it. Perhaps there was a playbook they were following, put together by an organization that they used. Anyway, it was really good. Like, it looked like somebody had some training to this, and it looked like a very specific type of thing if you've had that training. Anyway, Cackle's got up. So they're really good at the initial access fundamentals. But what they're not good at is the other things that necessarily wouldn't be part of a operator team. So like managing the hosts and making sure the keys get recycled and that the SSL or TLS key or certificates get rotated periodically. All that stuff is usually somebody else's job, and they're usually not good at it. So that's there. So they break in really well. They accomplish the task. When they have their people, like their main people on it, they just get into the target and they do pretty well. The problem is that if you're running a business, you can't scale that. And this is a business for them. They're trying to like actually get money out of people. So we at Redacted, we started tracking them. Sean and Hallie's talk was much better at this. I'm just gonna hand wave over that part. But essentially we enumerate the infrastructure and we find the people and start to reverse engineering. Okay, so first victim, June 2022. Leak site starts in July afterwards. We publish a blog in September. Malware Hunter team has the first sighting of them openly in public, so I want to give recognition there. Shortly after that, like days after that, we published our blog and then pushed it out there and got that. But in between September and January, it was kind of good times for BianLian. They were just making money. They're breaking into things. Their encrypter was working. People were having panic attacks. It was good times. But then the encrypter got released. You start to see weird, I wouldn't call them passive aggressive notes in the ransoms, but definitely active aggressive. They were very irritated that their stuff got broken, which I can understand. But eventually they had to just give it up. So like their encryptor doesn't work, they can pop it. And encryption's a big pain anyway, as far as the ransomware author. It takes a lot of time. So now they just steal data and then try to sell it back to you. So that's the other big thing. The other big tactic that they changed is that instead of doing all of the access and operations on target themselves, they started using affiliates. So we've started to see them advertise inside of some of these darknet markets, asking for affiliates to help them expand out their business and giving them a cut of the proceeds and all that good stuff. Standard malware operations. This is another BianLian dancer, if none of this makes sense. Okay, so the business model from the first part was compromise the target, install your tools for persistence, exfiltrate the data. Very important to exfiltrate the data first before you encrypt. This is pro tips for ransomware people here. Okay, once you do that, well, I guess if you have the key, it doesn't matter. But anyway, then basically you encrypt the data to force the conversation. You have the awkward conversation where you negotiate with people, and then all of the communication is done through this chat server called Talks, which is an open source encrypted system. Once payment is received, they would typically send you a decryptor executable. and then you could use that to decrypt the system. And does anybody notice, like with ransomwares, how they're like oddly concerned about customer service? They're like, we will help you and handhold you through the entire decryption process and that sort of thing. And it's like, do you know what I'm upset about in this transaction? It's like, it is not that. Like, okay, anyway. Different cultures? I don't know. Probably should read a book and find out. But all right, so now they're on to single extortion, which is their stuff got broken. We'll go how it got broken, and technical details. Now they just exfiltrate data and threaten to release it. And this avoids having to do a lot of the decryption support, which was kind of weird to begin with. And now affiliates do most of the work. What this has meant is that instead of having just BianLian tag tool sets, now other hacking tools are starting to come in and be tagged as part of the whole process too. So you'll see on some other reports from research places, I'm making some really awkward eye contact right here. They'll say that they're affiliated with other ransomware and malware tools, but that is not the case. They're just having affiliates in and other people are using their tools and bring it in. That's a pro tip. Okay. So what we're going to look at here are going to be the executable file artifacts. We're going to look at the backdoor, the encrypter. We'll look at how that got broken. And we'll talk vaguely about the decrypter and some of the listening posts. Generally from the code, this is written in the latest version of Go. Time of deployment, it looks like there's a CI/CD system. It seems like it's an Ubuntu 18 something system that they're using to build the executables. And what they do is that they build a custom executable for compromise. So when they target an actual organization, they'll custom build a piece of malware for you, which sounds a lot more ominous than it is. It's basically changing a text string inside of it, but it's good. Okay, usually Windows and Linux. However, fresh off the presses, I've got some Mac OS malware I got to look at when I get back to work. All right, so when you load a Go sample inside of your disassembler, the key thing that we're looking for are the symbols. So this is binary ninja, but don't worry to make things confusing. I'm going to switch to IDA in just a minute. But what we're looking at is the symbols. And in both of these, all these tools, there are symbols that are basically like, here are the local variables, here are the functions that you're going to call, anything like that, like strings that will sometimes show up there. But really what we care about are the functions. The first sign of the problem here is that there are no names. Well, there are names, but they're like sub and then some hex stuff, which is not very helpful. And if you look at the executable, like there's no obfuscations. Like the strings are all there. All the APIs are there. It was basically just a bug in a lot of the disassembler tools. So what you have to do is that you have to learn about the Go internal format for building executables and then repair it. So, or you can just take some scripts. So what you're looking at is the Go PC linker table. Go PCLN tab is what it's sometimes called. This stores the internal names for variables, functions, anything internal inside of your function that you could possibly want to know the name of with a debugger or some sort of logger afterwards. So everything was changed. The only real difference between the malware sample I was looking at and some of the other ones that worked was the version. So the linker table had changed slightly. There was another field that I believe another field was added. So it was just a matter of getting that fixed. There were some very good, if you're looking for an explanation of how the Go PCLN tab works, their Sentinel Labs has a tool called Alpha Golang. These are a couple of IDA Python scripts that now work with the newer versions of Go. So all of the pull request is submitted and everything, and they're still maintaining Alpha Golang, so it didn't just fall off into language, into nothing. So far right now, as far as the disassemblers, IDA Pro gets the gold star as far as reversing Go malware, just because it actually pulls it apart and makes sense of it. I would prefer this be binary ninja, but you know, writing disassemblers that support Go malware is real low on the product priority list for a lot of places, except for IDA Pro. Okay, so once you get the imports restored, what this gets you is like a lot of really nice things. So in Go, if you want to import a library, a lot of times you can just identify the GitHub repo that you want to pull the data in from. So in this case, there's this Cardianos, I don't know if I'm pronouncing it correctly, but it's a service manager for Windows. So if you want to write an executable and have it start and stop through the normal Windows process, you can use this. It's super handy. I didn't know about it before, but now I use it too. So like you do learn stuff from reverse engineering. It's pretty good. And then there's a couple of other things that are inside of there that are real interesting. There's this thing called MIMUX, M-I-M-U-X. And if you've ever done Go programming and you've ever looked at any sort of multiplexers, HashiCorp has one called YAMUX, Y-A-M-U-X, yet another MUX. Apparently they took it and modified it slightly so that you can arbitrarily execute code and some other things. The other big component that they make a lot of use of is this SOSO. It is a SOX connection and proxy server. So they use this for a combination both on their listening points to provide the SSL encrypted communications, but also to connect back and forward commands. So it's proxy aware. So anyway, like once you get the imports restored, this is what a happy import looks like inside of Go. We've got names, we've got main things, and especially what we're looking for is anything that says that it's like main related. And so once you get started looking at this, like actually reversing it, the negatives are that you get missing imports in pretty much everything, except for the later versions of IDA Pro. They do a little bit better job, but it's always going to be behind the curve. It's a little bit difficult to identify the author-developed code, but there's some tools out for that. The positives were is that the strings were intact, and then the imports, once they were rebuilt, it was just basically reading code at that point. So it was fine. So code extraction was possible, and that sort of thing. So once we got everything apart, we started to see some real interesting strings. And so I prepared this eye chart here so that some of you who are getting advanced in age, say in your 40s, you can use this as a reflection point about whether to go to the optometrist. But okay, that was a long explanation for nothing. Okay, so we got the Go build ID up top. That's important. It's probably a Go program. Over here, inside of each one of these programs, we have a lot of VCS identifiers. So like it says VCS equals Git. I know Git. I know where that's going. And it's got this revision. And it turns out that if you have an open GitHub repository, you can take those revisions and do this really amazing searching across the entirety of GitHub and find it. But wouldn't you know, if you have any private repos inside of GitHub, rest assured, they will never, ever disclose that to any authorities whatsoever. Like, they will not search for a hash for you at GitHub. So what I'm saying is that their privacy is really good. It's crap for doing these investigations, but everything else is great. But the VCS times inside of here seem to be pretty accurate. So this 428 is a very popular time that comes up. You also see lots of projects here. So in this case, the strings, it says that it's a home admin is where it was built. Thankfully, they didn't use their personal name, but they're calling it the SOX, and then you can see that they have an out directory, and then they organize it based off of the IP address and port that the implant goes to. So each one of these things has its own operation. Over here, you can see that they have very, very poor judgment, and they're using snaps to build their code, which is generally not fashionable these days. But if we look at the other strings, we also see some of the compiler flags where we get all this. And you'll notice that none of these have any sort of commands to strip out symbols or anything like that. So everything is pretty much there. Looking at the assembly, this is where a lot of the internal configuration, like this is the internal configuration for a lot of these samples. I don't know if you can see this, but in a very odd, awkward read color, there's a address and a port. And over here on the left, we have an IP address and a port. And all these things are like super old, so they're not active anymore, but maybe somebody's hacking from the audience. So command and control is all routed through a SOX proxy. This is typically some compromised box that they have on a remote system. So Over here you see an EC2 address. Other times you'll see DigitalOcean boxes. It's just whatever they can get a hold of and install their proxy software on to start doing this. And then typically there's some TOX communications that are there. So, but attacker issues commands and it forwards data over the connection. Can also send binary code to be executed. As we'll see here, this is a little bit awkward and not completely the complete side of the picture. If you want to look at the code loading capability, it is in main pointer program start. In this SHA-256 here, so you're gonna have to go on the YouTubes and look at pixelated stuff or email me or text me, whatever. But basically what this does is it downloads a blob of data, loads it into memory, and then executes it as a normal Go routine. But it's inside of here. There's also remote SOX control, so essentially everything is done inside of this main connect for SOX. This is the callback function that's in there. This gets swapped out if the binary is asking to do something else. All commands are base64 encoded, so they're pretty easy to decode and look at it, but there's not really much to see unless you capture the traffic as it's happening. Okay, so there's a flaw in the encrypter. And this was good because this encrypter, like it seemed like it had a problem because you could do some cryptanalysis on it and see that like things weren't entirely random. So we were getting there, and I'm really glad Avast just like ran with this because they seem to have better crypto people. There was also a really great security scorecard blog post about this that actually detailed all the things you could possibly want to know about crypto and like why the problem was. But like at the end of the day, the problem is that they didn't use public key crypto. They used a static key inside of their executables, and that's how victims were able to pull it out. So there's a very good scorecard there, but this just basically broke them. And they were real mad about it too. It uses the Intel internal AES instructions, but none of this is all, like in software development, there's a couple of truisms that I thought were taken for granted. It's like, number one, I thought we got over our EBCDIC conversion thing, but like watching that last talk, it's nope, still here. And then number two is that you should actually never roll your own crypto. You should always use a crypto library. And if you can't use a crypto library, then steal somebody smarter than you that has done it correctly. And that's the technique that they chose here. Like they actually stole the code, we found the code that they stole. It's got the same flaw and that sort of thing. So this basically just took it out. And I don't know what the difference is, like why you wouldn't put the effort into like just making that correct. But my impression is that they're more on the operator side, like the reaching out and hacking into things skill set, not so much the making backdoors and implants, which is a definite different skill. Some people are good at everything, but not usually. Okay, so that was kind of where we are right now. They had a hard pivot. Nothing was working, or everything was pretty much working. Reverse engineering was basically looking for some static offsets inside of there, and then you could identify the code base, the set, where it came from, and how it was going. And then the BianLians got a little tricky. They started to apply some obfuscation, and they used this Go module called Garbler, or Garbled. Has anybody used Garbled before? Yeah, I haven't come up with it either. I haven't come in any mitigations for it, but I got a quick hack in. So what this does is it strips symbols out, it takes any of the strings that you might find useful and then encrypts them or encodes them, like encodes. And then basically makes it a little bit different. And essentially the problem that it causes you, the reverse engineer, is it makes it difficult to figure out who wrote the code that you're interested in, and finding that code is hard again. So we have no strings. Our crutch is gone. We're very sad. About to start drinking to get over this. But then we look at some research out of Germany by a very smart gentleman named Daniel Plomin. And I'm really sorry if I mispronounce your name. He might actually be watching the stream. But this is great. This is a thing called mcrit. Basically, it's a min-hash code research. Basically, it's a min-hash tool for doing fuzzy function code matching on executables. So Without going into the algorithm enough for you to understand it, the way that it works is that it takes the mnemonics of the it takes the mnemonics of the instructions that are being executed and then builds a representation of the execution that way instead of just looking at strings and hard-coded data offsets inside of it. It's great. He wrote a whole dissertation on it. Like, I can't do this in like 20 seconds up here. It's really good, and like it's readable. He's just the nicest guy. He's been super helpful. Like, he's even accepted my bad patches. It's been great. Okay, so this is good software. And basically what it's implementing is the min hash and pick hash fuzzy matching methods for identifying similar code. The idea of this is that you set up an encrypt system, you import all the common libraries and all the common sorted malware that you have. And then what you do is that you submit new samples to it, and it's basically like a cape or a cuckoo sandbox without the execution and that sort of thing. But then it tells you how similar things are. And so there's a couple of features that are very, very helpful inside of here for the BianLian case that I'll go over. This is not like an expert usage of this, and it's definitely nascent and very good, but I've had really good luck with it. Okay, so this is an encrypt screenshot. So what I've done is I've uploaded every single BianLian sample that I have, which is like 300 by this point, and then the brand new ones. And then what I'm trying to do is just figure out, can I identify what family they belong to? And so what's really nice is that right out of the gate, encrypt does a pretty good job of identifying that this new sample that I submitted is an actual old, or is related to an old BianLian sample, and it actually matches something like 3,300 of the functions. And then also it matches 3010 on the min hash, pick hash, and then it's also identified 2,200 of the libraries. So this is all great. It's all pulled this out, identified it. I can go and look at other samples to see if it's actually there and verify it, and it just saves me a whole bunch of time. And so if you have a new sample that's not being picked up by AV and you're like, WTF is this? It's a great way to get you in the neighborhood. Okay. The other nice thing about encrypt is it does all of the library matching. So one of the goals that they started out with is that they wanted to have a more robust system for developing FLIRT signatures. FLIRT is IDA's fast library for identifying runtime or routines. I believe that's it. Anyway, function finder. So if you have a stir copy, it'll say this is a stir copy instead of you having to figure out like what that new XMM instruction is. It does all that for you. So it identifies it and it tags all the functions inside of there and makes it very good. So in this case, it identified the two libraries as mingw, so that's the GCC compiler for Windows. A lot of functions were shared with that. And then the second one was Golang, which is another, basically the libraries that are added inside of there. So right out of the gate, we're able to strip out a lot of the content that was causing problems. Okay, so fast forward to January 2024. Looking at these, they're garbled. The strings are jumbled. They're hard to read, and I'm despondent. I'm in a bad mood. And then along comes encrypt. And so I've already got all of my malware, or all of my old BianLian samples inside of there. And I'm trying to like figure out number one, what component is this? Is it a backdoor, or is it a listening post? Is it one of the the backdoors, or is it the actual encryptor, or something new? And none of that's in there. But what was really nice about this is that you can take that new sample that has obfuscations applied to it, put it into encrypt, and then it gives you an idea of what you're actually looking at. So now that I'm up on the stage, I'm sorry, this is completely even unreadable for me. I'll post the slides so you can see it later. But allow me to hand wave it up here for you. Up top is my unnamed sample. So I didn't assign a family to it, so that's why it's identified like this. Turns out it matches great with another sample that's in the same set that I found. And then you kind of go down the list of shame here. And so we've got win.bandit, win.doja, and a whole bunch of these other things, and eventually we get to BianLian. And you might wonder why all those other programs have been included inside of there, and it's for two reasons. Number one, they're using Go. That's one of the reasons. And then the other thing is that they're using a GCC variant to compile themselves, so they're being identified as similar. So already it's pulling out the toolchain and making that a little bit easier. Looking at the code, like once you get past all the obfuscations and you skip do all that, it's just normal. Like no AST changes have been made. The actual function and flow of the program is exactly the same. It's just the strings are garbled, and anytime you access a string, it's put in a decoder right before it, which is normal. So without any changes, we're actually in a pretty good place to be able to do this, to identify the code. And minhash and pickhash are pretty good algorithms for identifying these things. So we can actually go into a lot of the data or dive into it and actually look at the functions, because one of the things that you don't want to do when you're like actually comparing some of these functions is, well, you got to verify that they're the same. So what you don't want to do is you don't want to be verifying that there are two library calls that you're trying to identify, because basically what that means is that you're making a signature for a library call in the future instead of the actual sample. So there's a little bit of verification. It's got a very good method for looking at it, but what's really nice is on the screen, if you can see my little mouse right here, it's got a pick hash here. And next to it, you can see all the other malware samples and families that have been identified along with this. And so I can't, like, not really a good way to hover right here, but if you do, it's BianLian. And if you can actually take one of those pick hashes and say, now what other samples inside of the corpus, and there's probably about 200,000 samples in the corpus right now, what other samples match this? And then basically what it did is that it'd be nice if it actually like said names and that sort of thing, but in this case it's like just the sample ID. All of these sample IDs are old, recent, like newly changed, pre-2024 malware, and then the new malware with like easily changes so you can see what's moved. Once you find that you have a sample, so in this case, I found one sample that was just leaping out at me and really going there, what you can do inside of encrypt is start to use this 1v1. So has anybody here used bindiff in the past? Yeah, it's pretty great, huh? Saved a lot of time. Made it like you're really trying to figure out how to productize that thing. But it good. Like Halvar did just an excellent job with it, and then Google did as Google does and destroys things. Well, now I'm depressed. Anyway, encrypt works the same way. So it shows the perfect matches, which is what you want. It shows the slight differences where there's been some obfuscations, and basically gives you everything that you need. The only problem is that it's a manual process to convert between the two sample sets. So you got to copy some of the names over and that sort of thing. But that's just Python coding. We can fix that pretty easy. And so what you have now is that you can directly link and correlate samples together to be able to get that. So, we took an unknown sample that had some garbled and obfuscation to it. It had nothing added to it. We ran it through encrypt, and now we have symbols that we can actually go and start doing our reverse engineering with. So check out encrypt. It's really great, amazing. Okay, so as far as concluding this talk, the BianLian code base is actually fairly static. It does not look like they're doing development on it much at all, other than applying some obfuscators periodically. Binary diffing is basically how you combat somebody taking your strings away. Most of the changes occurred in 2022 to 2023, which really makes me seem like they had a developer then. But for now, like, I guess one of the open questions I have is like, what was the big cause for the change to affiliates other than scaling the operation? And then how did that change everything? Also, look at encrypt and any other bindiff tools. There's a couple others that came out. Ghidra just released the NSA's internal identification suite, which it's still just amazing that any of that gets declassified at all. But it's excellent. I've had a chance to play with it. The only problem is it's garbage Java, so it makes you feel like you're writing on a mainframe. And then the Montreal, gosh, I'm having trouble remembering the name of it. One of the universities in Montreal is very big on reverse engineering as well, and they have a new binary diffing thing out at scale that works pretty well too. So go ahead and check that out as options, but that's how you reverse Go malware, or at least how I did this one. Any questions?
So yeah, this is Q&A portion. Yeah, it's a little touchy. We don't have anything on Discord right now. I'll check again in a few seconds. But all right, over there in the back.
Yeah, why does Go have its own procedure table?
So the question is, why does Go have its own procedure table?
Why does Go have its own procedure table? I'd imagine it's because they could have used the internal mechanisms for it, but I think by building their own internal one, they give them a little more flexibility as far as portable operations. But I'm just guessing. It does make it a little bit easier as far as debugging and finding those sorts of things through the PC table. But like if you're writing malware, it's actually a really bad thing to have all your stuff called out in this open environment. So it's like pros and cons.
Hey, guys, if you want to have a discussion, please take it out to the hallway. Yes, over there.
That's a great question.
What was the name of which tool, sorry?
The question was, what is the name of the bin diffing tool that was right after Ghidra? I believe it was McCabe University, but I think that does not feel right at all. I feel very awkward saying that up here right now. But if you talk to me and give me 5 minutes to Google, I can get you the answer to that. It's there. Is it good?
Anybody else on the aisle? So the three things for functional.
So the string tables that they maintain in the Go binaries, are they per function or they're like executable wide for all the functions that are there?
Oh, so the three tables that are maintained. Yeah.
So the question was, is the PCLN table, right? Is that maintained per function or the entire executable? And the question is entire executable is what it's typically inside of there. So there's probably a lot of nuance inside of the Go development environment, but everything that I've seen, it's program-wide.
Anyone else? Okay. Thank you again.